So good evening everyone, and welcome to the third of today's Festival of New Events 2021. Just to let you know, there'll be a very brief Q&A after the performance. It gives me great pleasure to introduce Christo Squier, Subatomic, born out of a King's College London artist residency, composer Christo Squier and experimental particle physicist Dr. Teppei Katori are joined by a host of instrumentalists to explore this fascinating subatomic world via composition, sonification, projection, and performance. Some pieces are built using pre-recorded scientific data as inspiration. Others embrace entropy and improvisation by using mobile cosmic ray detectors or a feed from the Super-Kamiokande observatory in Japan. So please give a very warm welcome to Christo Squier.
The universe is full of great mysteries. You may think the greatest, most perplexing mysteries exist way out there, at the edge of a black hole or inside an exploding star. These are the highest energy objects in the universe, and we still don't know how they work. However, great mysteries of the universe surround us all the time, and that's what we're going to explore this evening. Fragments of atoms are constantly raining down on us, sailing straight through our bodies, and they're passing through you at this very moment.
Cosmic rays travel the thousands of light years from the deep universe, from the explosion of stars, it's called supernova, or from the black holes, or from some unknown high-energy object, either high-energy star or high-energy galaxies. There are many kinds of cosmic rays, and these cosmic rays are subatomic particles, and these are arriving to the Earth all the time, everywhere. And some of them reach to the surface of the Earth, or here, right now. We are receiving so many subatomic particles of cosmic rays right now. So all of today's music is either inspired or used the actual data from cosmic rays, the message from the universe. cosmic rays and subatomic particles are smaller than atoms. They are only recently discovered in the early 20th century, because if you want to see them, you need a very special equipment. And many things about cosmic rays are still in a mystery. Most of the primary cosmic rays from the universe collide with the air atom, like this movie. It's just gone, but maybe you saw it. So the most of the primary cosmic rays collide on the air layer, but this collision with the oxygen or nitrogen atom produces a lot of secondary particles. And those shower, because cosmic ray is high energy, so they break up atoms, or it also creates new particle by this collision. And because of this shower of secondary particles are arriving on the surface of the Earth, and we are receiving those showers all the time. And here we have one cosmic ray detector, which we call the cosmic watch. So the cosmic watch is designed to see these cosmic ray particles. So it's made by the small scintillator. It's a material which emits tiny amount of photons by the penetration of the radiation, and then the photon sensors. And then this signal is you see by this oscilloscope. So every time when you see the peak, yellow peak, that's the detection of cosmic rays. Okay. These cosmic rays, the most of the particles we see on this surface are called muons. And maybe many people never heard of muons, because the muon doesn't make any material. The proton and the neutron makes a nucleus, and the nucleus and the electron makes atom, and the atom and atom makes molecule. So muon is another type of subatomic particle which doesn't make any material. It's very similar with the electrons, but 200 times heavier. It doesn't make any material, so it's not everywhere. And so why the nature has muons, we still don't know yet. So these muons penetrate this detector, and it produces tiny amount of light, and that is seen by the sensor. And this signal is converted by this other device to the MIDI signal, and that signal is used to control the color of this room. So you might notice this room color change blue to red, red to blue. So this is done by these cosmic rays. So these cosmic rays penetrate your body all the time since you are born. But they're harmless. However, there's a speculation. The cosmic rays are responsible for making life on Earth. Like DNA may be made by the collision of cosmic rays and atoms, but we don't know yet. Strong cosmic rays sometimes destroy electronic device, and this happens all the time in outer space, in the satellite. It doesn't happen very often on the surface, but sometimes. So cosmic rays are so elusive, but they exist everywhere.
Just to add some Teppei's comment about the lighting, just in case you're curious, all the floor lights and this rack here on top, those are the ones that are constantly being tuned. You just got to change them. Constantly being controlled by this lighting. Jin Terrio on baritone. Charlie Jolly on bass clarinet.
Cosmic rays and subatomic particles are so elusive. And it's so hard to see them, as you know already, if you need this kind of device to see muons. Among them, neutrinos are the hardest particle to observe. So neutrinos have a nicknames. It's called a ghost particle because it is so difficult to observe, and it's everywhere. And they penetrate everything, even more than muons. So just as a number of neutrinos, how many neutrinos we have here right now, so more than 100 billion of neutrinos are passing through your body every second. And you feel nothing, of course. So observation of neutrinos is the hardest, and the observatories to see neutrinos are so special. And there are only a few of them in the world. So Super-Kamiokande is one of them. That's what you are seeing right now in this picture. The Super-Kamiokande, this is a 40-meter water tank, which is saturated by the purest water. It's ultra pure water, which even you can't drink. And it is surrounded by so many extremely sensitive light sensors. It's called photomultiplier tubes. It looks like a light bulb in this picture. And also this detector, the observatory, is located deep inside of a mountain to avoid all noise. And here is myself on a boat inside of the Super-Kamiokande. This is a fortunate experience because this tank wasn't open 12 years. But we needed something to repair in 2018, so many scientists had a chance to go inside to work on or take selfie. The collision of neutrinos and atoms are so rare. And we see roughly a few neutrinos per day at most by these observatories. And when a neutrino collides water molecule, it creates an extremely weak light. And these lights are so weak, and of course you can't see by eyes, but these lights are so weak, so even they behave like particles. And these are called photons. So sometimes neutrino makes only one photon, which is the smallest unit of the light. And these detectors is meant to see this one photon. These photons are recorded, and the information of time and the numbers are converted to the image you are seeing today and in the music.
So you're probably wondering, okay, how the hell does this come to this? So I'm going to try and explain a bit about the process for building this music. We just got a very powerful one there. I mean, it doesn't get old. They've been on all week, and you're like, oh, there's another one. The blue ones are the powerful ones. The orange ones are the gentle ones. Anyway, so we built some bespoke software, or a chap called Chris Ball built some bespoke software for us, and we began the process of turning data into sound. Now, sonification is a very kind of idiosyncratic process. Part of the challenge is part of the challenge was retaining the links to the data and where to let go of the to let go of the rigidity of the data and let myself play a bit more. There's a huge variety of ways we could have done this. Tonight's music is a mixture of stuff that's very rigid and very fixed, as in the chords that we pulled out from Super-Kamiokande at a particular time. I didn't mess with them at all, so I only used the notes I was given and the chord sequence I was given at a particular timestamp. Other times I granted myself a lot more freedom and just used certain ways that the chords came out as just inspiration and went off and played. So Kamiokande is a huge cylinder, as you've seen. It's big enough to fit the Statue of Liberty inside. Normally it's full of water, as Teppei said, so he was very lucky to get inside there. This is how we decided to sonify the data. So we are pulling live data from Kamiokande. There's a source online where we can extract the data and play with it in real time. We divided up the cylinder into 8 slices. We applied a scale to it. We used a whole load of scales and keys to get different results. Some really, really crunchy, some dissonant, some a bit more pleasant. But overall, it was completely unpredictable, as you can imagine, what it does, because cosmic rays are one of the most random things, probably the most random thing in the universe that we know of. So as you can see, we sliced it into 8 slices. We applied the notes. The height of the cylinder is the pitch, and the intensity of the energy is the velocity. So this particular instance, you see there's the epicenter is the red area, and it's kind of like a kind of gun firing through a cylinder. So as you've got the kind of entry wound, and that would produce, in this instance, a really low kind of cluster D7 flat 9 chord in that instance. So that was part of the process of extracting the data, but at the time I sort of kept the subject matter. I wanted to keep that link to the subject, this sort of receiving this information from up above. It was a really exciting process to be extracting data like that. I made sure to timestamp whenever I recorded the data from the software. I'm going to show you the software in a bit. So I'm just going to show you a couple of little chunks, because I didn't develop a lot of these pieces there. It's the first time we've ever played them. In fact, as of a few days ago, they've ever been played. So they're all still pieces in development. But here's a couple of little things that they're just like little tasters. So this piece is called Hopped, and we pulled out the data between 11:20 p.m. and 11:41 on Friday, the 21st of May, and the scale we had ascribed to Kamiokande was F-sharp Lydian, and this is what came out. Another little taster, between 1:56 and 14:10 on the 25th of July, while the software was set to B-flat major, we got these chords. Spicy.
So cosmic rays are everywhere, all the time. It's literally billion of them are passing through your bodies right now. But some cosmic rays are so special, and it happens very few. The one good example is the neutrinos coming from the explosion of the star, called supernova. Supernova emits neutrinos, but this was observed only one time in human history. That was 1987. Because to see them, the supernova has to be close enough in the Milky Way, within the 60,000 light year, which is very near for us. And in this period, like last 1,000 years, there are only 6 supernovas happen in the Milky Way. And happen to be one of them, or 1987, we have a technology to see neutrino, and there happened to be the time this detector was operated, and we saw it. So how lucky we are. Oh, because of this, by the way, they got so much more funding, and that's how they make a Super-Kamiokande. So these are all random. And these phenomena in the universe are so random. And because of this, the cosmic rays are random. So we know the cosmic ray coming from everywhere, every time, but you can't predict where they're coming from, and you can't predict when they come. So this cosmic ray detector, cosmic watch, it's detecting the cosmic ray, but this process is also random. That's how the light changed randomly. This randomness is so important for nature and also our human life. The example is like a computer simulations. When you perform simulations, you need a random number, but this random number has a quality, so you need a best random number, the most random number. So how do you make the most random number, or how to maximize randomness, is an important mathematical questions. So it's people keep studying in mathematics to make the most random things. However, the randomness of cosmic ray beyond this. And some people said the cosmic ray is way more random than any random number human can make with the biggest supercomputer. So this randomness of the nature is beyond human intelligence.
We're going to embrace some of that randomness now, and we're actually going to pull some data, hopefully, from our software. This is where the data's coming from right now. This is the real-time monitor. It's kind of a bit blurry, but this shape is a cylinder expanded. It's Kamiokande over a net, and you can see that you have the cosmic ray activity, which is being transmitted online all the time. Although we only get the dregs of the data, it's making readings a lot, right? We only get a transmission maybe every 30 seconds to a minute, but in reality, it's reading things all the time, super quickly. I've tried in earnest to access the deeper level of Super-Kamiokande. I've been in a long email threads with Teppei, kind of speaking to scientists to get to the real juicy stuff. But at the moment, we just access this online. So we pull this into this bespoke software that was built, so we've got a variety of different keys that we can apply to. We've put it's in B flat major at the moment, although it does just do whatever the hell it wants to do. And we're going to pull this into Logic and run it through some spacey sounds, because that's inappropriate. We could run it through just some string samples, and I'll just give you an example of what it might do. So I'm going to hit play, and it should, within a minute, start pulling the data from that website. There we go, we've got our first chord, which is very pleasant. And this software is, I should point out that all of the visuals that you're seeing, they've all been screenshots from this software. So all the spinning dots, they're all a visual representation of Super-Kamiokande that I've screen recorded and given to my friend Pete to manipulate and create all these pretty visuals. So all the visuals are built from the data as well. Oh, we got a loud chord there. So it's just, we've had another one triggered, and we've got a new chord. So that's all very good and well, but we want a sort of space jam. So let's run it through some weirder software. And we're going to embrace that randomness now. We're pulling the chords are going to come from Kamiokande. The dynamics are going to come from the cosmic watch here. So we're going to be watching for the changes in the lighting to affect the way that we play. So we'll just see what happens. So enjoy. I didn't think we were going to get one. There was so long that it didn't change. Like just in rehearsals, it was like it's changing all the time. But that's randomness.
Yeah, I just thought my cosmic ray detector was broken. I was a bit scared, but yeah, exactly like Christo said, it's a randomness. We know on the average, roughly this 10 centimeters square, roughly you have a few cosmic rays per minute. But this average can be deviated, so it doesn't mean you always have few cosmic rays per minute. So. Okay. So neutrinos. Neutrinos are ghost particles and invisible. So we only see particles generated by neutrinos. So once the neutrinos collide with a water molecule, so many high energy particles are produced. And these particles create a shock wave of light that is called Cherenkov radiation. And photons, which is a particle of light, are emitted in a ring shape. And these photons are seen by light sensors, photomultiplier tubes. The Super-Kamiokande use more than 10,000 of photomultiplier tube, but they use the very special one. Each of them is a 50 centimeter size of, it's a vacuum tube. So it doesn't explode, it's implode. And these are so sensitive. So sensitive to see the photon, and how much sensitive it is. So if you have a flashlight, if you have a torch on the moon, you can see it from here. So that's the amount of photons we are talking. In this, right now, 1 centimeter square, it's roughly 2 times 10 to 16 photons, which is million times 10 billions. But this device is designed to see 1 photons, which is coming from 1 interaction of neutrino atom. So light made by neutrinos are so weak. And at most, you can see a few photons by Super-Kamiokande, the photomultiplier tubes. And these photons are detected on a different time, and some sensors see the more photons or stronger light. To understand the detail of these natures, the scientists, we use lots of simulations. So simulation means it's a virtual world. So we construct the real world object in a computer. To understand the neutrinos, we also program a real Super-Kamiokande detector in a simulation, in a computer. The Super-Kamiokande simulation data showed how the Cherenkov radiation ripple around the detectors. And these simulated data sample, it lasted only 20 nanoseconds. So 20 nanoseconds is the speed of these neutrinos, and then interaction happen, and then the photons are generated and seen by the detectors. So it's too fast. So we stretched to make it slow down this shockwave view, and so that you can see the gradually lighting up the detectors.
Yes, we took this 20 nanosecond event in Super-Kamiokande and converted each of these moments to MIDI, which talks to the music software. You're probably all musicians, so you probably all know what MIDI is. But MIDI sends data to trigger music software. We got it in the software and stretched it, slowed it right down. And then I would just comb through these crazy rhythms and listen for ones that interested me. And at first it kind of sounded to me like popcorn because it's just so random, so it sort of fizzes. And then I took a few interesting slices of this, extracted it, added a melody to it, and then gave it to poor Jin here to transcribe. So the next couple of pieces, there's a rhythm at the end of the next one. It's a little sketch, but again, it's a work in progress. The rhythms at the end that Jin and Charlie on sax and clarinet are playing, that's completely derived from this particular event. And the piece afterwards, the rhythms throughout are from this data event. So I hope you like it.
So today's performance is based on cosmic rays and subatomic particles. So these use simulated data or real data or some inspiration from these. So these cosmic ray and subatomic particles are so elusive, but it's everywhere. It's always next to you, but still we don't know. We don't know so many things. We still don't know how this highest energy object works in the universe. And there are so many other mysteries, such as dark matter, dark energy. It could be related to cosmic ray we see. So the study of cosmic ray is continuing, and our journey continues.
So this is going to be our last piece. Thank you so much for joining us today. We hope you feel as inspired as we do by this fascinating subject matter that connects us all and connects us to the great unknown out there. What's next for the project is we're hoping to keep developing and refining it and maybe building some sort of installation that lights up in real time. Some sort of structure is definitely on the wish list. But thanks so much for coming, and this is the last piece. It's called Conduit.
So, I mean, as we're like super short on time, I just had no problem at all. It was, I thought, really amazing. And what was so interesting to me was how effective the format was of sort of lecture and music, and how actually the interaction between the two kind of changes your perception of the other almost. My question, I suppose, to you was how this project kind of came about in the first place, and what drew you to it?
Well, I've always been fascinated with cosmology and astronomy since, well, not always, since about sort of 18 when I got into Carl Sagan. Any Carl Sagan fans out there? So I've always been drawn to that sort of world. And then I met Teppei at, of all places, an activist brass band festival in Boston.
Wow.
We stayed in touch, and when Teppei moved to London to work for King's College, he told me about this bit of funding that King's College had to collaborate with in the Department of Physics. So we came up with some ideas and applied, and then it went from there.
So I think that when we spoke, Teppei, I think it was yesterday, I sort of asked you about what an experimental particle physicist does, and asked you to explain it to me as if I were a small child or a golden retriever. I won't ask you to do that now, but I was curious about, you were talking about muons, and that we are able to detect these, but we don't really have an idea of exactly what they are. And I'm curious to know, because I suspect that probably a lot of scientists have certain belief systems about things that they don't know. And so just out of curiosity, what do you think they are?
Well, so these are fundamental building blocks. So we used to believe atom is the smallest things, but now atom has hundreds of them, so it looks like not fundamental. So atom have to be made by something else, then nucleus and electrons. And then the nucleus is made by proton and neutron. And now you know proton and neutrons are made by quarks. So you go down and down, split more, and the muon belonging to this so-called elementary particles, the smallest level. So I'm an experimentalist, and my belief is phenomenology, which is the branch of philosophy. So the things given by the nature is what it is, and all I can do is measure and find more. So the structure is very ugly, and a lot of theorists, like smart theorists like Stephen Hawking or these people, are not satisfied how the world looks like. Einstein as well. They are very unsatisfied with this situation. And we are, like last 100 years, we are keep finding a new particle. And now we used to have 100 of atoms, and we thought it's ugly, so it should be something fundamental. But now we have a quark and a lepton, and these are also around 100 now. So, something not quite fundamental.
Okay. I have absolutely no follow-up to that response, which is kind of funny. Christo, I'm wondering, with your use of sonification, like what sort of guides those choices to you? Because there's a kind of sort of an arbitrariness to using sonification in a way. So when you're using it, are you sort of thinking about it in the same way? Like, what's the point of it?
For me, the crux is that all of those bits of music wouldn't have sounded the way they sounded unless I'd done all that weird stuff beforehand.
Right.
Yeah, so that, for me, it's inspiration. I mean, the subject is inspiration, but
Sure.
having some rules where musically you don't normally have. I mean, there are rules in music, but not necessarily in composition, depending on how you look at it.
Sure.
But I found it strangely freeing to use this extraction of data as a springboard to send me off in directions that I may not have gone in. I'm still working out ways that I can be more rigid with the data, and
Sure.
perhaps ways I can be even freer. We've only been working on this for a few months, so it's still very early days for me. But I'm still working out how sonification can keep inspiring my process and getting interesting results.
Sure. Well, it certainly inspired, I think, all of us today.
Yeah, I want to add one thing. So this project happened during the pandemic, So
Right.
we have to move plan A to plan B to plan C and D, like delta and then eta, mu variant in this way.
Right.
So
We had one big idea is to have 10 of these cosmic watches attached to 10 musicians moving around, and they're like slaves to the cosmic watch. So whenever the light flashes, they play. So we thought, I mean, it might not sound very good, but it'll probably look quite cool. These like flashing, bleating musicians like controlled by the heavens. So maybe we'll do that next time.
Cool. Well, we look forward to seeing it. So I just wanted to thank both of you and also to thank the ensemble as well. So give it up for these guys.